Hello and welcome to Mathematics for Machine Learning. Today we're talking about summary statistics of random variables. Their first two moments, namely the expected value and the variance. Why do we need summary statistics? Well, say we have a large number of examples, xn, from some probability distribution p of x. And now we don't want to use always all of these n examples to make useful statements about the distribution or the population of these random variables. For example, we might want to give information about typical values, about the spread of the distribution, about, say you have multidimensional samples, how they co-behave. That's what summary statistics are good for. Some examples of summary statistics are the mean of a variable, the variance, giving idea of the spread, the standard deviation, which is similarly to the variance or a measure of spread, but in the same units as the values of the variable itself, the median, which is somehow related to the mean, the covariance in case we have multiple variables, so how do they vary together in relation to each other, as well as correlation. These summary statistics, they are deterministic functions of the random variables, so of the distribution. They are not random variables themselves. Estimates of the summary statistics might be random variables because we're computing them from the data. But the true summary statistics is a fixed deterministic function. Of course, we want these functions to be as useful as possible and basically use them to make statements about how these variables behave. Let's start with the mean. Now say you have examples for some random variable. You might be interested in knowing what's the average of this, or the mean. This is given by the so-called expected value. It's written as e of x, and for discrete probability distributions, it is given by the sum over all possible values that the random variable can take, summing up this value, weighted by the probability of seeing this value. So it's a weighted sum, a weighted average. So say all values are equally likely, then it would just be a normal average. So say we had n different values, they're all equal likely, then we would basically take all of these values, sum them up, and divide all of them by n. But of course, they could be differently likely. So in general, this is the weighted sum over the value times its probability. Now for continuous random variables x, we replace the sum by an integral. So we're integrating over the range of the random variable, for example, from -infinity to +infinity, the value times the density of this value. You can think of the expected value as the center of mass of this random variable. Remember, we're taking the weighted sum. The integral is just a continuous version of the sum of these values, weighted by their probabilities or the density. Let's look at some properties of this expected value. So the first property that we look at is linearity. Say we are given a series of random variables x1 through xn. Then the weighted average of these xn. So if we sum them all up, multiply them with some scalars alpha I, and maybe add some scalar beta to them, the expected value of the resulting random variable is given by the weighted average of the expected values of the original xi. This weighted average, obviously, is a random variable itself. So we're essentially taking n different random variables and constructing a new random variable by taking the weighted average, each weighted by the corresponding alpha I, and then we add the scalar beta to it, and the resulting random variable has expectation equal to the weighted sum of the expectations of the individual random variables xi plus beta. Note that linearity even holds if all the xi are not independent. If all the random variables xi are independent, we additionally get the product rule for the expected value. So the expected value of the random variable that is given by the product of n independent random variables is equal to the product of the expected value of these n random variables. Now in general, say we are given only a sample from some probability distribution, we typically do not know the expected value of this probability distribution. However, what we can do is we can use these samples to get an empirical estimate of the mean of this random variable. And this estimate is given by the average. So this empirical mean, which we typically denote by x bar, is just the average, 1 divided by n, times the sum over all of these realizations xn. Now note that here we are not multiplying each of the xn by the probability of observing it, because we're working here with a sample. Because the probability of each value is already reflected in the relative frequencies of observing this simple value. So once we have a sample, we can just estimate the expected value of this distribution by averaging. Now note that we're here computing a function of the random variable, a function that depends on a sample. So the empirical mean is a random variable itself. And it is not equal to the expected value, but it is an estimate. So the idea is that it's a value that gets close to the true expected value. In fact, it gets closer the more samples we average over. So if we let here this capital N go towards infinity, it should go to the true expected value. There could be different notions of an average. We've already discussed the mean, the expected value, which is the center of mass of the probability distribution. But of interest could, for example, also be the median. Now the median is the middle value of this probability distribution. So it's the value where 50% of the values are smaller and the other 50% of the values are larger than this median value. Consequently, it's also the 50th percentile of the distribution. What does it mean to be the 50th percentile? Well, it means it's the value that you would get where the cumulative distribution function is equal to 0.5. So that means that 50% of the probability mass lie on the right side and 50% of the probability mass lie on the left side of this median value. In comparison to the mean, the median tends to be more robust to outliers than the mean. You can think of it, if you have some extremely large value, you're not actually taking them into account. So if you just say took the largest value and just multiply it by 10, it's still the largest value, so the median is unchanged by that. However, if you would compute the mean, you would take that value, if you multiply it by 10 or by 100, into account when you're averaging. So the mean would be moved. The third interesting value could be the mode of a distribution. So the mode of a discrete distribution is the value that is most frequently occurring, in the sense that it has the largest probability mass in the discrete case attached to it. In the continuous, it would be the value with the highest probability density. So in the continuous case, we of course have to be a bit careful, because in principle the mode would never be actually occurring, because you basically can go infinitely close to it, but it's the point that has the highest probability density. As an example, let's look at the mixture of two bivariate normal distributions. So our P of x is given as the weighted average of two bivariate normal distributions. That means we are multiplying the probability density function of a bivariate normal distribution with a mean vector and a covariance matrix with a weight 0.4 and adding another bivariate normal distribution weighted by 0.6 with a different mean and a different covariance matrix. However, they're both evaluated at the same point x, and see that the two weights, they add up to 1. So both of these are normal distributions, so they themselves are normalized, so they integrate up to 1. So the integral of this normal distribution over the whole range of the possible x values would be 1. Now we're multiplying that with 0.4. So that means that the integral of this first component would be 0.4. And similarly, the second component is also a bivariate normal distribution, which is normalized. So it also integrates to 1. We weigh this 0.6. So this part integrates to 0.6. And if we add up these two distributions, the integrals add up. So the whole thing will add to 1. So the first part integrates to 0.4, the second one to 0.6. Together, they're 1.0. Now they have, as we said, different means and different covariances. What does this mean? Well, what we have here is two different components. Thus, as we said, the expected value of this mixture distribution will also be the weighted sum of the two expected values. So this is the expected value of the first component. Here we have the expected value of the second component, and we weigh them by the corresponding weights. So that means that the expected value of this mixture distribution will be 0.4 times 10 is equal to 4, plus 0.6 times 0 is 0. And for the second component, 0.4 times 2 is 0.8, plus 0.6 times 0 is still 0.8. So the expected value of this mixture distribution will be the 0.4 or 0.8, which is different from these two expected values. Now, if we look at actually data that is sampled from this mixture, then we will get the distribution over here. We see that all the points that we get fall in these two so-called modes of the distribution. So they're all spread around the expected values of the original components. So this would be the 0.00 here. Here we have the 0.102. And you see that all the points that we get from this mixture fall around these two original expected values. However, the joint expected value, which we said is 0.8, is actually in a region where there are no points close by. So it's a low density region of the distribution, of this mixture distribution. So the expected value, while it's the center of mass of the whole distribution, doesn't need to have a lot of density itself. Note that this mixture of two Gaussian distributions is different from building a random variable as the weighted average of two Gaussian distributions. The mixture is bimodal because we are here averaging the probability density functions, not the random variables. As a result, you can think of the mixture as sampling from either one or from the other Gaussian distributions, whereas in the weighted average we would sample from both and build the average. Both have the same expected value. However, the mixture is bimodal and the weighted average is unimodal, centered around the expected value. The expected value is of course only one of the different notions of average that we have discussed. The other ones would be the so-called modes. So the modes are the points that have the highest density. We see that we have two different modes for this distribution. If you're looking for the mode, the point that has the highest density, then it would actually be this point 10.2 here. That is the point that has the highest density itself. It's this star here. However, there are two local modes. And the interesting thing is that if we look at the one-dimensional marginal distribution, then the mode that actually has, in the two-dimensional case, the lower density has, in one case, actually the higher density. And the reason for that is that we are averaging over the other dimensions. The one dimension we are marginalizing out. So we're averaging over this dimension here. Because there are so many points spread out over here, they all collapse into the same region, and we actually get a different global mode for the one marginal distribution. So while for the bivariate distribution, this would be the global mode, and this would only be a local mode. For the univariate distribution on this one dimension, this will be the global mode. For the other dimension, now we are averaging over this dimension here, we see that these actually collapse and we don't get two clearly separated out modes anymore, but only a single one here. How about a median? Well, for two-dimensional distributions, there is no clear median. Why is that the case? Well, the problem is that we don't have a unique ordering. While for a single dimension, we can always say whether a point is smaller or larger. That's not the case if we have two coordinates. For example, if we want to compare the point 3,0 and 2,3, by default, it's unclear which one is larger or smaller, because this one is larger in the first component and this one is larger in the second component. So we somehow have to define what the ordering sign means. For example, we could define it only based on the second component. Then this point would be smaller than this because the second component is smaller than the second component of the second point. We can not only take expected values of random variables, but also expected values of a function of a random variable, which turns out is a random variable itself. And the expected value of a function g that goes from R to R of a univariate continuous random variable x that comes from the density p of x is given by, well, it's the expected value, and here we're making clear in the notation that we're averaging over the distribution of this random variable x, the function g of x, and it's given by, well, the integral from -infinity to +infinity of gx. So this integral is actually going over x, right? So let x go from -infinity to +infinity, computing g of x and weighing that with p of x in our integral. And similarly, of course, for discrete random variables, we can again give the expected value of a function of x by taking, instead of the integral, the weighted sum. So we're taking a sum over all the possible values that this random variable can take, compute g for this value of x, and weighing this g of x by the probability of observing this value of x. What else can we say about expectations of functions of a random variable? For example, because linearity of the expected value holds, if we take the weighted average of two functions of x, the expected value of that will be the weighted average of the two corresponding expected values. Let's look at the derivation briefly. So f of x is equal to a constant a times a function g of x plus a constant b times a function h of x. Then the expected value of this combination f is equal to, in the continuous case, the integral, as we said, of f of the random variable x weighted by the density of this random variable x, and it's the integral over the variable x. This is equal to, if we plug in a times g of x plus b times h of x, equal to the integral, again, the integral over x, of a times g of x plus b times h of x, weighted by the density of x still. As a and b are constants and we have a sum here, we can actually split this up into two integrals where we pull out the constants. We have a times the integral of g of x weighted by p of x dx plus b times the integral of h of x p of x dx. And these are the two definitions of the expected value of g of x and h of x, respectively, weighted by these constant a and b.